Welcome back. The objectives of this video is to explore logarithmic functions as inverses of exponential functions. And we're going to start here with an application problem in sample 4. Since every logarithmic function is the inverse of an exponential function, we can think of every input value of an exponential function as the output value of a log function. Consider your savings account that you want to know the year when your initial investment will double. Consider the following scenario. Suppose you invest $2,500 in an account that pays an annual interest rate of 6%, compounded continuously. We know the balance in the account after t years can be found by a model of A sub t, or A of t equals 2,500 e to the 0.06t. So that would be our PERT formula. Use the table of values for A of t to graph a log model that will display the account balance as the input with the year as the output, and estimate how many years before your $2,500 initial investment will double. Honestly, with what you know about B, we could do the rule of 72, and since we're getting 6%, we ask ourselves what's 72 divided by 6 is 12. So we already know that this is going to be approximately 12 years. We'll use our data and our tables to find a better answer than that, but we already have a sense of what that's going to be by using the rule of 72. Well, let's go ahead and put this function into our calculator and use our table of values, and we'll fill in our table here for t and our A of t for up to 15 years. So I have my calculator out, and I go into the y equals menu, and I can enter my 2,500 times e to the 0.06x, and when I do e, that's the e above the natural log function, and I enter that in my calculator. And I go ahead and think about my window. So I'm starting with $2,500. That's going to be my initial y, and that's going to continue to grow. And my x's are years, so those can start at 0 as well. And now it's just a matter of how many years. My table asks for 15. So let's take a look at our window here. So our x's, I went from 0 to 20 years, and I counted by 2. My y min, $2,500, and I went to a y max of $7,500, and I counted by 500s. Then I'm going to go to my table. So second table set, and I'm going to start my table at 0 and count by 1s, and this will give me a table of values. So then I can go above the graph key and go second table, and sure enough, now it gives me my x's and y's for that function. So for 0 years, it's 2,500. For 4 years, $3,178.10. For 8 years, $4,040.20. It asks for 12 years, $5,136.10. And 15 years, $6,149. And we also can see from our table of values that we're going to reach $5,000 somewhere between 11 and 12 years. It looks like about 11 and a half years. So we've really answered a lot of our questions, and now we'll go ahead and fill in these answers in our table on our notes page. So I filled in my output values for all of those input values of t, and for answer B, we can see here that it will take about, as we saw from our table, it will take about 11 and a half years to double our money. That's consistent with our rule of 72. And then in this third column, they ask us to find the inverse. So we're flipping our x's and y's. So our ordered pairs here are just going to flip. So the first order pair here is 2,500 and 0. Our second ordered pair is 3,178.10 and 4. and so forth. So we'll fill the rest of that in. So I've completed my inverses and finished off those ordered pairs. And now we want to graph a logarithmic model that will display the account balance. So this are the inputs for our logarithmic model. This would be my inputs for the exponential model for PERT. So I'm going to flip all these. So you can see our x's and y's on our table have flipped. So our time now is on our y-axis, and our amounts are now on our x-axis. And we can input the ordered pairs from column 3 and plot those. So I plot each of those ordered pairs, and we end up with this logarithmic model. I missed my points, but you get the general shape of that curve and our logarithmic models. And then wrapping that up on the doubling, we can see according to our model, $5,000 will take around 11.5 years. Certainly we could have graphed y equals 5,000. I don't know if you can see that, but we could have graphed y equals 5,000 on our original, and we would have gotten the x value and been able to flip our x's and y's to see that. In example 6, we're given our function f of x equals 2 times log base 2 of x plus 1 is our function, and we want to graph our function. Since we're working with log base 2, our goal here is to get x plus 1 to become things that are 2 to a particular power. So we would love x plus 1 to become 2. We would love x plus 1 to become 4. We would love x plus 1 to become 8. So I'm going to force the x values that give me x plus 1 equals 2, x plus 1 equals 4, and x plus 1 equals 8. And then I'm going to graph those. So when x is 1, I get 1 plus 1 is 2. Log base 2 of 2 is 1 times 2 is 2. So my output is 2. So when I enter 1, I output 2. And now I'm going to choose an x value of 3, because 3 plus 1 gives me 4. So when x is 3, I get 2 times log base 2 of 4. Well, log base 2 of 4 is 2, and 2 times 2 is 4. So now when I input 3, I output 4. So I can plot that one. And then I use x is 7, so I can get log base 2 of 8, which is 3, and 3 times 2 is 6. And so I can plot that point. So now, and of course, if I put 0 in for x, log base 2 of 1 is 0. 0 times 2, and I get 0. So now I have my logarithmic function of that particular graph. Now, if we remember our transformations, we might know that this is a transformation of 1 unit to the left. So we will end up with a vertical asymptote on our logarithmic function, and that graph will look something like that. In B, they ask us to find the inverse algebraically, so that means flipping our x's and y's. So I'll do the inverse in red here, and I'll flip my x's and y's and solve B. So now I get x equals 2 log base 2 of y plus 1. Divide both sides by 2, which then gives me x over 2 equals log base 2 of y plus 1. And now I'm going to convert from logarithmic form to exponential form. So I'm going to convert forms here. All right. And I'm going to go log base answer equals exponent. So the exponent on 2 is x over 2. So 2 to the x over 2 equals y plus 1. I subtract 1 from both sides and get 2 to the x over 2 minus 1 equals y. And that is the inverse function. Question C says graph the inverse of x Well, that looks like going to be a tough exponential to graph. We could do that with our transformations. I think it's easiest just to flip our x and y ordered pairs. So I have the ordered pair 0, 0. That's going to stay 0, 0, so I can put a red dot there. And then I have an x of 1 and a y of 2, which means I could have an x of 2 and a y of 1. And I had an x of 3 and a y of 4, so now I could have an x of 4 and a y of 3. And then I had an x of 7 and a y of 6, so now I have an x of 6 and a y of 7. And my vertical asymptote is going to become a horizontal asymptote at -1. And I get a graph that looks like that. So there in red is the inverse of x. And then finally it says to analyze. So it's asking for the domain, the range, our end behavior, our asymptotes, and our intercepts for each of our two functions. So we'll go fill all that in and answer those questions. So the domain for our function, our valid x's, go from our vertical asymptote at -1 all the way out to positive infinity. Our y's go from -infinity to positive infinity. Our end behavior as our x's go to positive infinity is positive infinity. I do question the limit of our function as x goes to negative infinity, because x really can only go to -1, or we're approaching -1, but then that limit would be negative infinity. We do have a vertical asymptote at x equals -1. That's that end behavior, that limit. That's why the limit can only go to negative infinity. We do have our intercepts at the origin at 0, 0. And our concavity, that is a graph that is concave down, that is increasing at a decreasing rate. Our domain for our inverse function is -infinity to infinity, and our range is -1 to infinity. And this should make sense to you because an inverse function, we flip our x's and y's, so it should make sense that we flip our domains and ranges. The limit as x approaches positive infinity for our red, that is also going to positive infinity. The limit of our red as we go to negative infinity, now that one is going to negative infinity. We have a horizontal asymptote at y equals -1, and again an intercept at 0, 0, and that function is concave up, and it is increasing at an increasing rate. It is an exponential function. This one, it's growing exponentially. So that wraps up our exploration of graphing logarithmic functions and its inverse and the application problem, and we'll get some more practice with this when I see you in class.